Electric potential due to a uniformly charged disk. A uniformly charged disk has radius capital R and surface charge density sigma. Part A, find the electric potential at a point P along the perpendicular central axis of the disk. Part B, find the x component of the electric field at a point P along the perpendicular central axis of the disk. Now, if we look at this uniformly charged disk, the area element in this disk can be taken as 2 pi r dr, where r is at some radial distance from the center of the disk. And you can see that we have an even smaller area here, which will have sides dr and r d theta when we have a small angular displacement d theta. So this will be like a rectangle which has an area r dr d theta. So our dq will be inside this small area. And this dq, which is like a point charge, is at a distance square root of r square plus x square from point P. So x is the distance of point P from the center of the disk to the position of point P. So that's our distance. So this is our perpendicular here. So this is a right triangle, and we have this distance square root of r square plus x square as the hypotenuse of this right triangle. So what is this dq, our small charge element in this case? Dq is sigma times dA. So you can see that I'm not using this dA anymore. Basically, I'm using the small area element as r dr d theta. So this dA is not what I'm using. All right. So in that case, I can write dq as sigma r dr d theta, where dA is now r d theta multiplied with dr. Obviously, when you integrate over this angle theta here, you will get a factor of 2 pi, so this dA would turn into 2 pi r dr. So it's actually the same thing when we consider this ring of charge. Okay, so we can write the potential dV due to the charge dq as k dq divided by the distance from the charge to the point of interest, r square plus x square square root. So if I substitute for dq sigma r dr d theta, this will be k times sigma r dr d theta divided by r square plus x square square root. And in order to calculate the total potential at point P, I have to integrate this over the whole area of the disk. So this will be an integration from 0 to capital R, the radius of the disk, and 0 to 2 pi for the angle. So you will see that I will have r dr d theta. Sigma is a constant because it's uniformly charged disk. And then I have the distance r square plus x square square root. So the integral over the angle theta will just give me a factor of 2 pi. So this will be equal to 2 pi k sigma integral from 0 to capital R, r dr divided by r square plus x square square root. Now, in order to perform this integration, I will let u square equals r square plus x square, so that 2u du will be equal to 2r dr when I differentiate both sides. So the 2's will cancel. You can see that I have to substitute for r dr u du. And what do I need to substitute for square root of r squared plus x squared? Square root of r squared plus x squared is equal to u. And now when r is equal to 0, I can see that u will be equal to x. When r is equal to capital R, u will be equal to x squared plus capital R squared square root. So these are basically the new limits on the integration that I have to perform. Okay, so the total potential at point P will be equal to, for K, Coulomb's constant, I'm going to substitute 1 over 4 pi epsilon 0. So this is 1 over 4 pi epsilon 0 permittivity of free space. That's K. Then I have 2 pi sigma. So this is 2 pi sigma. The integral with the new integration limits x to x squared plus capital R squared square root u du, r dr was replaced with u du, and u at the bottom, so these u's will cancel and I will be left with the integral of du. So this will just give me, basically, when I see that this 2 pi cancels the 4 pi, giving me a factor of 2 at the bottom, sigma over 2 epsilon 0, sigma over 2 epsilon 0, integral of du. What is the integral of du? It is just u. So u maximum is x squared plus r squared square root capital R squared minus u minimum is x. So this integral gives me u, and I just need to evaluate at the limits. So I can write my final answer. Potential at point P is sigma over 2 epsilon 0 x squared plus capital R squared to the power 1/2 minus x. So that's the final answer for part A of the question, potential at point P. The second part of the question was x component of the electric field. Now, how do I go to electric field from potential? Electric field is minus the gradient of the potential. And also notice that I have a symmetric situation here. So if this creates an electric field on this axis, in this direction, there will be a symmetric charge here that will create an electric field like this, so that the y components will cancel. This is exactly the same situation that happened here for the uniformly charged ring. The y components cancelled. So from symmetry, I can simply write the y component of the electric field will be 0 anyway. So Ey is 0 due to symmetry. What is the x component of the electric field? Then using the gradient operator, that is minus derivative of the potential dV with respect to x. So it's minus dV dx. Now I have to take a derivative here. So I have minus sigma over 2 epsilon 0. Now I take the derivative of inside. From the derivative of this term, I will obtain a factor of 1/2. Then from the derivative of inside, I have a factor of 2x. X squared plus r squared differentiated with respect to x gives me 2x. Then I have x squared plus capital R squared to the power minus 1/2. 1/2 minus 1, that's minus 1/2. Derivative of the second term, x is, with respect to x, is just 1. So this is minus 1. you can see that the 2's will cancel, and I will be left with the x component of the electric field, Ex at point P, is equal to, now if I operate this minus sign inside, this is going to be sigma over 2 epsilon 0, sigma over 2 epsilon 0, 1 minus, because I have operated the minus sign, x divided by x squared plus capital R squared square root. So that completes my answer to part B of the problem. So let's see what I can say about some limits for these results. So for the discussion part, the first limit I'm going to look at is what happens if the radius capital R is much greater than x. You can see that the x component of the electric field in that case will become sigma over 2 epsilon 0. Why? Because if R is much greater than x, and this x can be ignored, x divided by R goes to 0, so this becomes sigma over 2 epsilon 0, which is the answer for a uniformly charged infinite plane. This is an answer we're familiar with, that we have derived, we have obtained before using Gauss law. Now I want to look at another limit where x is much greater than R, so that I'm at a very far distance from this charge. So what do you expect? At a very far distance, this disk will turn into a point charge. So I expect that the electric field will be the one due to a point charge. So let's see if that happens. In the other limit, when x is much greater than capital R, the electric field x component, sigma over 2 epsilon 0, let's rewrite it in this form. It was 1 minus x over square root x squared plus R squared. So if this goes upstairs, square root x squared plus R squared minus x divided by square root of x squared plus R squared. So I write it with the common denominator, x squared plus capital R squared square root minus x divided by x squared plus capital R squared square root, and I'm looking at this in the limit R is much less than x, or R is approximately equal to 0. Now for this term, square root of x squared plus R squared, what happens when R is much less than x? This can be written as, if I take this into x squared parentheses, x times 1 plus R squared divided by x squared square root. Okay, so if the x goes inside, this would be x squared plus R squared, x squares would cancel, and I would obtain the left hand side. Now there is an important result I know from Taylor's expansion, Taylor series. 1 plus y to the power n is approximately equal to 1 plus ny for the limit y much less than 1. So this is a result I know from Taylor series expansion, basically. So I recall this result in order to understand the limiting behavior here. So this tells me that when y is equal to R squared plus x squared, this can be approximately written as x times 1 plus R squared over 2x squared. So this n is 1/2 here, in the limit R much less than x. Okay, when R is much less than x, we have y much less than 1. So y is R squared plus x squared. Okay, so with that, the electric field x component becomes sigma over 2 epsilon 0 For the top part here, I'm going to write x times 1 plus capital R square over 2x square. So I have replaced this square root with this term, with the Taylor series expansion in this limit, minus x divided by x times 1 plus R square over 2x square for the bottom part. And this is going to become, you can see here I will have an x minus x, x's will cancel, I will be left with r square over 2x square. This r square over 2x square is much less than 1, so that can be ignored. So basically I can see that in the limit r is much less than x, 1 plus r square over 2x square will be approximately equal to 1 for r much less than x. So this will become then sigma divided by 2 epsilon 0. For the top part I have r squared over 2x, because this is x plus r squared over 2x. X's will cancel for this part. But then I have another x coming from the bottom because this is replaced with 1. So this becomes r squared over 2x squared. R squared over 2x squared. And now I recall the charge density sigma for a uniform charge distribution will be equal to the total charge Q divided by the total area of the disk pi r squared. So the electric field X component then will become the charge density Q over pi r squared divided by 2 epsilon 0. So this will be Q divided by 2 pi epsilon 0 capital R squared. That is this term. And now I have r squared over 2x squared, capital R squared over 2x squared. Capital R squares will cancel here. So I will be left with k 1 over 4 pi epsilon 0, which is k, Coulomb's constant, total charge q, divided by x squared, which is precisely the answer for a point charge q. So my expectation is fulfilled. I can see that in this limit, the disk behaves like a point charge. Okay, so let's summarize what we did here. We're considering a uniformly charged disk with surface charge density sigma, so our answer can have sigma in it. We want to know the electric potential at point P at a perpendicular distance from the center of the disk along the central axis, and the X component of the electric field. First, we find a small area element, which is the r d theta multiplied by dr. So r dr d theta, that's the area of this region. So area of this region multiplied with the uniform surface charge density sigma gives us dq, the small charge element in that region. So that's our sigma r dr d theta dq. And we know that a point charge has a potential at point B as dq divided by the distance, square root of r squared plus x squared, and that's because we are at a perpendicular distance, square root of r squared plus x squared to point P. This is a right triangle. We have the radial distance r from the center, x from the center to point P. So for dq we substitute sigma r dr d theta, then we integrate over all r values from 0 to r, so we cover all of these rings here basically. If we perform the theta integration first, this becomes 2 pi k sigma, so 2 pi r dr, it then basically becomes the area of this ring. So 2 pi r dr integrated over r from 0 to capital R gives us the full disk contribution. In order to perform this integration, we substitute for r squared plus x squared u squared, so that r dr is replaced with u du, and square root of r squared plus x squared is replaced with u, and the limits of the integration are replaced with x and square root of x squared plus r squared. Integral du is u. U evaluated at u max minus u min gives us our potential sigma over 2 epsilon 0 square root of x squared plus r squared minus x in parentheses, provided that we replaced our Coulomb's constant k with 1 over 4 pi epsilon 0. In order to find the x component of the electric field, we remember electric field is related to potential as minus gradient of the potential. Y component of the electric field at this point cancels from symmetric contributions on each ring that I consider here. So the x component is minus dv dx. I take a derivative with respect to x, and from the derivative of inside I have 1/2 x squared plus r squared to minus 1/2, and inside I have 2x, so I obtain 1 from the second term, x term, and this gives me, considering the minus sign here, 1 minus x over square root x squared plus r squared multiplied with sigma over 2 epsilon 0. Now I want to discuss this result when capital R is much greater than x. This becomes an infinite plane of charge. What would be the electric field in that case? This term would go to 0. I would obtain sigma over 2 epsilon 0, which is the result we have obtained using Gauss law. On the other hand, when x is much greater than r, then we are at a very far distance from this disk. It looks like a point charge at this very far distance. And what is the electric field at that far distance? So square root of x squared plus r squared minus x over square root of x squared plus r squared, in the limit r goes to 0. Square root of x squared plus r squared can be written as x times 1 plus r squared over x squared to the power 1/2, remembering that 1 plus y to the power n for very small y, much less than 1, is like 1 plus ny in Taylor series expansion. So this is replaced by 1 plus r squared over 2x squared for r much less than x. If I do this at the bottom and on top, I obtain from the top a cancellation of x's giving me r squared over 2x. From the bottom I obtain basically 1 plus r squared over 2x squared is approximately equal to 1 because r is much less than x. Only this x term remains, so this gives me r squared over 2x squared. Then I have sigma over 2 epsilon 0. If I replace my sigma with total charge divided by total area for uniform charge density, that gives me the final answer as kq over x squared, which is precisely the answer for a point charge.